Today we will explore volcanism, magma types, eruption styles, and the characteristics and classification of magmas. But what is magma? Magma is a term that refers to rocks that are partially or completely molten, including liquid, crystalline, and gaseous phases. In other words, magma is a melt with temperatures ranging from approximately 800 to 1200 degrees Celsius. It forms, is stored, or solidifies within the Earth's crust. When magma reaches the surface during an eruption, it is called lava. The main characteristics that influence magma are the weight percentage of CO2, the volatile content, and the temperature. These factors control how the magma behaves, including its viscosity, mobility, and the way it evolves during ascent and eruption. The weight percentage of silicon dioxide is used to classify magma into four main types according to its composition. Rhyolitic magma, considered acidic, contains more than 66% silicon dioxide. Andesitic magma, classified as intermediate, has a silicon dioxide content between 52% and 66%. Basaltic magma, described as basic, contains between 45% and 52% silicon dioxide. Peridotitic magma, known as ultra-basic, has less than 45% silicon dioxide. These differences in silica content play a major role in determining the physical and chemical behavior of the magma. The composition of magma depends on the most abundant elements in the crust, including oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, and hydrogen. Silica plays a fundamental role in magma viscosity. Silica tends to form polymer chains, and the higher the silica content, the longer the chains of polymerized silicate anions. Polymerization is determined by the bonding between silicon tetrahedra. Low polymerization results in isolated or weakly linked tetrahedra, producing low viscosity magma, typical of mafic and ultramafic magmas. High polymerization creates three-dimensional tetrahedral networks, increasing viscosity, which is characteristic of felsic magmas. As a result, rhyolitic magmas, with more than 66% silica, are generally much more viscous than basaltic magmas, which have between 45 and 52% silica. Andesitic magmas, with silica content between 52 and 66%, have an intermediate viscosity. Volatile content also affects magma behavior. Magma contains dissolved gases such as water, carbon dioxide, hydrogen, sulfur, sulfur dioxide, chlorine, and fluorine. Water can dissolve in magma either as molecular H2O or as OH groups, which break the silica network and reduce viscosity. The higher the volatile content, the lower the magma viscosity. This creates a volcanic paradox. At depth, dissolved gases reduce viscosity by breaking the silica network. Near the surface, however, pressure decreases, causing gases to exsolve, form bubbles, increase internal pressure, and sometimes trigger explosive eruptions. Temperature and crystallization also influence viscosity. As magma cools, crystallization increases, reducing fluidity. Higher temperatures decrease crystallization, making magma more fluid. Viscosity depends on temperature, silica content, volatile content, and degree of crystallization. Now let's examine the main types of magma. Basaltic magma forms from partially melted mantle rocks called peridotites, composed of olivine, pyroxene, and plagioclase. Basaltic magma has low silica, low volatile content, and high temperatures between 1000 and 1200 degrees Celsius, making it very fluid. Basaltic eruptions are the most common in the world, forming thin, extensive lava flows. Examples include Iceland, Hawaii's Kilauea and Mauna Loa, the Paraná magmatic province in Brazil, and the Deccan Traps in India. Andesitic magma forms from partial melting of the oceanic crust in the presence of seawater under high pressure and temperature, typical of convergent plate boundaries. Andesitic lava has intermediate viscosity and represents about 10% of surface volcanic material. Examples include Mount St. Helens in the United States and Krakatoa in Indonesia. Rhyolitic magma is silica-rich and volatile-rich, occurring mostly in continental crust. Its high viscosity slows ascent, forming thick lava flows, domes, and granite batholiths. Rhyolitic magma solidifies between 800 and 1000 degrees Celsius, has a reddish color, and accounts for roughly 10% of volcanic material. An unusual type of lava is carbonatitic lava, such as at Doinyo, Lengai in Tanzania. This lava is rich in sodium and potassium carbonates, erupts at low temperatures of approximately 510 degrees Celsius, and is extremely fluid, even less viscous than water. Lava can also be classified by surface texture and flow style. Pahoho is smooth, billowy, or ropey lava formed from hotter, more fluid basaltic magma. A is rough, jagged, and clinkery, produced by cooler, more viscous basaltic lava. Blocky lava is thick, slow-moving, and breaks into large angular blocks, common in andesitic and rhyolitic flows. Pillow lava forms rounded lobes when lava erupts underwater. The type of volcanic eruption is mainly controlled by magma viscosity and volatile content. Effusive eruptions involve low viscosity, low volatile magma. Gas escapes easily, lava flows smoothly, and broad low volcanic cones are formed. These eruptions are common in Hawaii, Iceland, and the ocean floor. Explosive eruptions occur with silica-rich, viscous magma that traps volatiles. When pressure becomes too high, magma erupts violently, ejecting pyroclastic material and forming steep-sided cones, domes, or spires. In viscous magma, gas bubbles rise slowly, and sudden pressure drops cause them to expand, forming pumice or fragmenting the magma into volcanic ash. Understanding magma properties allows us to predict eruption styles and behaviors. Silica content, volatiles, temperature, and crystallization all interact to determine whether magma will flow gently or erupt explosively, shaping the volcanic landscapes we observe today. Thank you for watching. Share this video to support our channel and subscribe. If you have any questions, comment below and I'll be happy to explain.